This is the 14th edition of this event, which was meant and still is to be a supportive activity for our PhD students. So the idea here is pretty simple, was to give our PhD students a sort of friendly environment in which they could present and discuss their papers, important the second bit of discussing all the papers, and also interconnect with young researchers from European universities, basically, okay? And that was the initial idea, that still is, and to do so, we wrap it up with a main speaker. You've seen in the emails and the previous information about the workshop, our good speakers. This year we have Bettina Klaus from the University of Lausanne. You'll hear about her. If you didn't Google her CV, which you should have, of course. If you didn't, don't worry, you'll know about her in a minute. Talking about doctorate in cycles mechanisms. The idea of having a main speaker, though, is not just to have someone to give you a wonderful lecture. She's going to stay here for the 2 days, so you should expect comments and remarks from her. And also, you should expect to take advantage of the fact that you have excellent researchers to ask her, to discuss with her, your own ideas about research. Because this is also about that. It's about having connections, discussions, and hopefully even maybe a good idea for a research project, which is a rare thing that sometimes happens. Okay? So, this is the welcome that I had to give you. Traditionally, this is given by someone from the rector office. Unfortunately, because of agenda problems, nobody can be here. That's the General Assembly of the University. We pick up the right date, as you can see. So, as I said, on behalf of the direction of the ECOSOS, me as director, Julia as co-directors, we welcome you. We hope that you have 2 very successful days. And I have to conclude with a bit of thanking, because we do science, sort of, but to do science you need support. Okay, so I want to thank to the committee members, the organizing committee and the scientific committee, which selected these dozen of papers that we're going to have. Actually, I have bad news. We have 11 papers. Someone dropped at the last minute because of health issues. I'll give you some more details later on, don't worry. He's okay, but couldn't make it. Anyway, so I want to thank the both committees for the work. I also want to thank the previous direction of the Research Center, because we joined in November, so that means that basically everything was done. It wasn't that hard. Okay, so I want to thank them both, Professor Jose Maria Arauzo and Cory Carles here. Cory Carles, Jesus, sorry. Sorry. It's not Cory Carles. Okay. It's Cory Vilella. So, anyway, so thank you both to them. And finally, I want to thank our financial support. As I said, you need money, but you also need people. So my last word is for the people who's been organizing this. You'll see there's a few people around, give you things, taking care of you. They are the ones really behind all this. Nothing can happen without them, so I want to thank particularly them for the work. And that's it, unless my co-director who want to say something. So thank you very much. Enjoy it. Yes, that's the one.
Bon dia i moltes gràcies a tots per ser aquí. No sé si ens veu bé, si no. Thank you very much for being here. Good morning, everybody. I would like to thank you all for coming to this 14th PhD student workshop on industrial and public economics. It is a pleasure for me to introduce you to Professor Bettina Klaus, who will make the keynote lecture, and he's going to talk us about celebrating the famous top trading cycles mechanism. We are now honored to have with us Professor Bettina Klaus, Professor of Microeconomic Theory at the Faculty of Business and Economics at the HEC at the University of Lausanne. Professor Klaus received her PhD from the University of Maastricht in 1998, and since then, she has built an impressive and truly international academic career. She has worked in the United States at the University of Nebraska, Lincoln, and at Harvard Business School, as well as in Catalonia at the Universitat Autònoma de Barcelona, and the Netherlands at the University of Maastricht before moving to Switzerland in 2009. Her research lies in the intersection of economic theory and social decision making. In particular, she focuses on fair division, market design, matching theory, and social choice theory. Through her work, she has significantly contributed to our understanding of how resources and opportunities can be allocated in a fair and efficient way, with important application in areas such as school choice, labor market, and public policy. In addition to her research, Professor Klaus plays an important role in the academic community. She is currently the president of the Society of Social Choice and Welfare, which reflects her international recognition and leadership in the field. Today, we are very pleased to have her with us, to share her work and insights with us. So thank you very much again, Bettina, for being here. And we
Muchas gracias, Corey.
Thank you.
Ok, bom dia. Bueno, he trabajado en Barcelona. No hablo catalán, pero hablo un poco castellano. So es un placer estar aquí. Thank you for inviting me. But in the end, my English is still better than my Spanish. I'm not using it much. In the coffee breaks, please help me practice my Spanish. But about research, I cannot really talk very well in Spanish. I prefer English.
You have good Spanish.
But even, my native language is German. I also cannot talk about research in German. It's very difficult for me to do that. So English is my native language for research. So my talk is going to have two parts. And of course, I am sort of aware that my research is not at the core of the research that people do at this conference. I'm not exactly industrial in organization or public economics. I'm matching and market design. But that research field has an advantage because some of the models are very easy. I'm not saying it's easy to do research in those areas, but the models themselves can be presented very easily. And I think I can give you some insights interesting to PhD students through the talk in terms of how you approach research. And there's a little bit of economic history here as well. So I am going to first start with this I'm going to stand. I don't want to sit, it's too static. I just put myself here. So basically, I'm going to give you a little bit of a survey concerning the famous top trading cycles mechanism. And of course, maybe you're saying famous? I've never heard about this. Now, it is relatively famous. I'm going to talk about this original paper introducing this so-called top trading cycles algorithm. It is famous because it was invented by mathematicians in a purely theoretical context, and later turned out to have huge applied impact. For instance, when talking about organ transplantations, kidney exchange. So one of the most important applications where this helped to design how people are reallocating kidneys. Well, what do you mean by reallocating kidneys? Well, what I'm referring to is the fact that there are people who need a kidney transplant, they're on dialysis, and they might even have a donor that could give a kidney, but they're not blood type compatible. So now all of a sudden we have a theoretical situation where there's a patient owning an object, namely they have a donor, but they can't consume that object. And now the question is, how could we reallocate, how can we trade these objects in a non-monetary way, that's very important in these health applications, such that we can help the patients get a new kidney. So you can think about what I'm going to talk in a theoretical context with respect to the fact that it has been applied, for instance, in the so-called kidney exchange market. Okay? The second part of my talk is going to talk about the general model of object allocation. But in fact, before I talk too much now, let me start with my talk. Now, I'm going to start with I would call it a classical paper. So I started developing this talk 2 years ago when the paper celebrated its 50th birthday. That is a long time ago, so there's some time that passed. So now, of course, I have to update my slides because I can't say 50 years ago, it's 50 plus 2 years ago now. And this classical paper is by Shapley and Scarf, and it's written in 1974. And most of you who say, that's even way before I was even born, this is a long time ago. Yes, sort of, it's a classic paper. Now, the model is simple, which is also why it lends itself to this audience. The model is such that we have n agents, and we have indivisible and heterogeneous items. Now, in the paper, the authors were saying these are houses. So this is why we call the model the Shapley-Scarf housing market. Even though housing markets really don't work like that, right? We're going to see that the real housing markets you face are completely different. But anyway, we have these n objects, and the point is that each agent owns one object. Hypothetically, you can think about your donor that you own. Now, agents have these endowments and they have preferences. And the preferences are the ranking of these objects. By the way, another example could be task allocation or allocation of courses. Like we teach a course, every professor teaches one course per semester. I mean, in many cases more, but that's an extension of the model. And there are established courses you teach, and at some point people feel like changing. And the question is, how do we allocate courses among professors? So, or even real housing, dormitory units, right? Maybe students at some point want to trade the dormitory rooms they have. They're in different buildings, they want to be closer to friends, stuff like that. So do you have preferences? They can be weak or strict. Agents can trade their houses, but there are no transfers. We are not doing auctioning, we are not paying money here, and that makes a lot of sense in many contexts. Course allocation, I mean, not going to pay Corey money for giving me her course, and for the kidney context, it's sometimes even legally forbidden to have monetary transfers. So basically, in the seminal article, these guys were looking at this model, but the reason was not to look at the model. The reason was, and I'm going to tell you what the reason they did this research was, they were actually interested in non-transferable utility games. Okay? So this is, I'm going to talk about that in a moment. I'm continuing with the model first. So basically our input is the preferences of the agents. I ask you, how do you rank these courses, and you tell me. You give me a ranking, possibly with the differences of these objects that we have. So we have weak preferences, we have strict preferences, and now a market or problem is the agents, the houses, and the preferences. Very simple model. There's a difference between weak and strict preferences as a domain. I might mention that, I'm not going into too much detail. An allocation is a reassignment of the houses. I just commute the houses, so we swap. An agent gets an allotment, it's just terminology. And for a coalition, I can just denote what the coalition gets by AS. So I have an allocation A, and A of S is the set of houses this coalition gets. Now, I'm referring to core concepts, and this is something you have encountered in your micro theory course, which I assume at least most of you might have taken at some point as part of the PhD education, you've done general equilibrium, I hope, or at least the base models there. So the core is a very classical concept as well. What we assume is in an exchange economy, the core is an allocation of our resources that we have such that no coalition can be better off by reallocating their endowments. And of course, this intuition is also true in this context, because basically what we can define is this blocking notion where we reallocate and are better off. And now you can ask, well, what does it mean to be better off? And there are two ways of modeling better off. One is by strong blocking. So a coalition can strongly block an allocation if the B of S is equal to H of S. So that means they propose an allocation where they reallocate their endowments. That's all that notation means. And second, all of them are strictly better off doing that. So basically, you know, this part of the room says, hey, I don't like this allocation. Let's get together and reallocate our endowments. You just run off with our endowments, which you can, because you own them, and be better off strictly. That's a strict block. And an allocation is a weak core allocation if it can't be strictly blocked. And you can also change this blocking notion, which then Ross and Postlethwaite later proposed, by making it weak blocking. Here you have to be, everybody in the coalition has to be strictly better off, but maybe I don't mind helping my friends to get a better course allocation. And maybe the blocking could also be that we run off, we reallocate our resources, and some of us are better off and some are the same. Nobody's worse off. So this is the weak blocking. And then if it can't be weakly blocked, you have a strong core allocation. Clearly the strong core is a subset of the weak core. So these are solution concepts that we know from general equilibrium theory. So this is just another reference here. And now we go back to our original paper. In game theory, you have two branches, non-cooperative and cooperative game theory. And as the part of the cooperative game theory, there's also the concept of a core of a cooperative game. I'm not going into the definitions here, that would take a bit too much time, but the idea is very similar than what I just presented to you. And the idea is, at the time, cooperative game theory was really popular, and lots of results were established for cooperative game theory. In particular, an existence result or characterization result when the core of a cooperative game is non-empty. And this result was established by Bondareva and Shapley separately. So it tells you, look at the cooperative game, if some balanceless conditions are satisfied, then the core is non-empty. And it's an if and only if statement. So Shapley and Scarf, these guys were very much involved in this cooperative game theory context. And Herbert Scarf actually was interested in extending this famous characterization of a non-empty core for cooperative games to the so-called non-transferable utility games. So transferable utility means we can transfer value, and non-transferable utility we have, like in certain bargaining situations, we cannot just freely transfer our value. There's some boundaries to that. If you wish, you can think of a bargaining game where you have a bargaining set imposed by the feasible solutions. So Herbert Scarf was interested in extending existing results to the more general context of non-transferable utility games. I'm not going to define those either. It's just important that he had in mind how far can we extend those results. And he wrote a paper where he actually characterized non-emptiness of the core for non-transferable utility games. And he was very proud of that result. So then, as mentioned here, there is the background story why he wrote the paper with Lloyd Shapley. So he recalls, I was very eager to find a cooperative game without transferable utility whose core could be shown to be non-empty using my theorem and not by any other method. So the guy wants to he extended a famous result and now he wants to illustrate it. So it's a clear goal why he wrote that paper. So by the way, again, this talk shows you a little bit what motivates people to do certain research and how it works out later. Okay, I still find it quite remarkable that this game is balanced without any additional assumptions on the preferences and therefore has a non-empty core. Okay, so he's very proud of this paper where he has this application showing the core is non-empty by his method and not by any other method. I gave a talk at Berkeley on this subject several months later and spoke with great pleasure on the use of my theorem on balance games. David Gale was in the audience and came up to chat with me after my talk was over. He said to me rather diffidently, I think that I have another argument that the core is not empty. And he told me about the notion of top trading cycles and their use in providing a simple algorithm which always found a permutation in the core. When I returned, I sent David a letter with the phrase, I'm terribly sorry to have to tell you that there's nothing wrong with your argument. So basically, Herbert Scarf had to declare defeat. His purpose of the paper was to show you can't show the core is non-empty, but with my wonderful theorem, which uses separating hyperplanes and whatnot, complicated stuff. And it turns out, David Gale sits in a seminar and says, well, I think there's a simple way of doing that that doesn't require all your machinery. We don't need MTU games, which is why I didn't introduce them, because we don't need them. So the thing is, David Gale proposes this algorithm how to solve these housing market problems in a very elegant way. And as you observed, he isn't even the co-author of the paper. So Shapley and Scarf included the top trading cycles algorithm and the result that it will always produce a core allocation in the paper. But David Gale did not want to be a co-author. He said, no, this is your paper, I don't need to be a co-author. And of course, David Gale didn't need to be brilliant guy. There has been a Nobel Prize in economics. Well, it's not a Nobel Prize, an original one. It's a spherical Rijksbank Prize of Economic Sciences, appointed to market design and matching theory, including Shapley and Roth. But Gale wasn't part of it because at that moment he didn't live anymore, and you don't give Nobel Prizes to people who has died. So he would have been a member of that for sure. I'm almost sure if he had been alive at that point. So here is this algorithm. It's very easy. Just imagine that you are an agent and you own an object. You have a house or a course. Now, if your preferences are weak, I just break ties. I make them strict. I just break randomly, it doesn't matter. Now, each house points to its owner. So your course points at you. It wants to be with you. Each agent points to his top house. So you in the room point to the person who has the course you want to teach. So I might want to teach Corey's math course, right? And now, basically, the point is there has to be a cycle. We have finitely many people, finitely many objects. Each has one pointing. And you can now just go, I point at her course points at her, she points at some other course, that course points at the owner. You cannot go on forever without returning to a previous agent and house, right? This cannot continue. There has to be a cycle. The simple cycle is the one where my object points at me and I point at my object. I immediately take it, that's a cycle. But then there can be bigger cycles. And the point is, the cycles we clear. Clearly we have found people who want to optimally swap their courses. And that's a top trading cycle, because in that cycle everybody gets the top object. So this is where the name comes from. But now the point is, once I do it, those people are happy, they leave the room, hey, we traded our objects. And you know what, we now repeat with the remaining agents and with the remaining objects. There can be still trades where some people get their second best object, right? Which is still better than what they have. So you just continue. So you repeat it until you clear the market. And then the output is the top trading cycles allocation. And this thing finds applications in many, many contexts. Of course, sometimes it has to be adapted. There are extra complications, as with kidney exchange. We cannot have a 100 people cycle. We need to limit that. That poses problems. That can be solved with research. But it's actually a good basis to do research in applications where you allocate objects to agents and where there might be some endowments. Okay. Now, I told you this thing has many, many citations. I didn't check how many, but just go and check. It has many citations. It finds many applications in many different contexts. I only give you a part of a survey, but you have at least 2 papers giving a little bit of a retrospective, taking the 50th birthday of this top trading cycles algorithm into account. So there are 2 survey papers here that came out in 24. By the way, there's something weird going on. I'm not going to put a conspiracy theory. If a lot of the good contributions concerning top trading cycles were published in a year ending with a 4, right? Of course, this is celebrating, so of course that's not a coincidence. But there's more. So here's just a very quick illustration. We have a red, a blue, and a green agent. They're all colored houses. They point at the house they want. As you can see, the red and the blue agent can clear a top trading cycle. The green guy doesn't get anything. And so basically you do the swap. While there's only one agent left, I can make this very, very complicated. I think you understood how this works. And I get an allocation. Now, again, back to the original paper. What is the main result of the paper? Well, the main result is that the core is non-empty. The core for this non-transferable utility game is non-empty. So we have a core allocation as I have defined it. It's even it's a strong core allocation for strict preferences. And it's the unique one actually. And on top actually there's something else wait, sorry. I need to point, this one. It's also a competitive allocation. So let me link it quickly back to general equilibrium theory. What is a competitive allocation? A competitive allocation happens when you sell your endowment and everybody buys the best bundle with the money they get when they sell the endowment. So this is a concept in an exchange economy. Same thing happens here. This top trading cycles allocation you can rationalize as a competitive allocation as follows. In the first step, people trade the best objects, right? Maybe other people wanted that. The green agent wanted another house. He ends up with something worse. You put a high price to the first step objects that are traded. So the first swaps, I sell the houses for 1 million. Now in the second round, whoever trades gives the objects a lower price. 100,000. In the third step, 10,000. In the fourth step, 1,000. I can put arbitrary prices. And now basically what happens is that when agents sell their endowment, they can trade with exactly the same people as with the top trading cycles algorithm. Because the more popular houses that were demanded more have higher prices. So it's also competitive equilibrium allocation. Now also these allocations are Pareto efficient. Of course, whenever I mention the name Pareto, and I talk just about general equilibrium, I have to mention that Leon Valrat and Wilfredo Pareto were working in Lausanne. At the moment not at HEC, they were at the law faculty, but those guys were holding the chairs for political economy in Lausanne several years ago. I didn't meet them. And these allocations are individually rational. You get something that's at least as good as your endowment. Okay. Now we can transform this algorithm into a mechanism or into a rule. And we do it by, when I say, so a rule always assigns an allocation for any input, for any preference profile. So that's a systematic way of solving problems. Shapley-Scarf housing market problems. So the top trading cycles rule assigns the top trading cycles allocation for each input. That's the idea here. And Ross had the good idea to say, well, you know, as economists, we are not only interested in efficiency, we are also interested in incentives. If you use this, what are the incentives for people giving you the right input, telling you the truth about their preferences? And he figured out that it's the TTC rule is good for incentives because everybody has telling the truth is a weakly dominant strategy. In other words, whatever you get when you tell the truth, no matter what other people do, this is encoded here, you tell the truth, RI, where other people tell what they tell, and you think about lying and you put an RI prime, you're getting nothing that's better. Lying does not pay off, right? So that's a very nice property. So we have incentives. Yeah, that's just a 2, it's not a 4. And BERT, here you have the 84. I mentioned to you there are many papers that are nice that end with a 4. I haven't checked whether that's over proportional or not. But BERT figures out it's not only true that a single agent doesn't have an incentive to misreport. It's even true for groups. So when I get together with Cory and you know some of you, we could try to manipulate by saying, hey, listen, let's coordinate our reports, and maybe by doing that we can be all better off. Now that's much stronger, right? And again, what does better off mean? Better off can mean we are all strictly better off. So this is written here. A rule is weakly group strategy proof if no group of agents can get together, misreport, and everybody in the group is strictly better off. And of course you can also say, hey, better off can also mean again, we get together, everybody, some people are better off and nobody is worse off. And then you defined group strategy proofness. So here a group misreports, nobody is worse off and some people are better off. There is a little bit of subtlety here because this is a statement on the top trading cycles rule being weakly group strategy proof for weak preferences. I can have indifferences. And you get the stronger group strategy proofness property when you have strict preferences. I don't want to comment too much about that difference because in practice we can assume strict preferences, if only because I make you report a strict ranking. Now here's another lesson for PhD students. This is an old paper. Some of you will also say, hey, I wasn't born then either. This is still very old. And this is a classic result. It's cited many times. And it's not wrong. So let me mention this is not wrong. However, fairly recently, those two guys, I think they're from Stanford, figured out that there was a gap, a mistake in the proof. So people cited, they didn't check the proofs, they said, yeah, it's probably, and it's true, it's not wrong. Huh? But they figured out, wait a second, they show that one of the proof steps, a critical claim in the paper, is wrong, and you can correct it, but effectively that means the paper did have a crucial mistake. You know, if a proof is objectively wrong, hypothetically the authors haven't shown the result. And they say, hey, there is a flaw, here's how you fix it, and they could publish that result. So it's true, but again, you needed to fix the proof. So what's the message? Don't believe things. In the end, at some point, you have to do your fact-checking yourself. And if you don't understand something, either you put time to learn it, and then you have learned a lot, or maybe you find a mistake, and then you can write a comment and publish it. I mean, yeah, sort of a little lesson here as well. Now we jump to a different approach, namely asking, great, this thing has great properties, it's strategy proof, it's period efficient, it's individually rational. I already mentioned these nice properties of the top trading cycles rule. But you could say, yeah, this is cool, what else does that? Is this the only way of doing it? Can we find out some other ways of doing it? And surprisingly, Ma is in '94, again the 4 there, see, is a guy who asked that question that nobody asked before, and he gives an answer, and this is a beautiful result. For strict preferences, actually the top trading cycles rule is the only rule that satisfies these 3 properties: individual rationality, Pareto efficiency, and strategy proofness. Incentives, efficiency, and minimal bounds due to ownership. One way of doing it, can't do it any other way. Now he has an extension for weak preferences. It's not so important. If you dive into the topic, you can look at that, what happens when you have differences. But this beautiful characterization is 30 plus 2 years old. Now, there's another thing you can do when you see papers with a result. When you write a proof, that's cool. You proved your result. If you do theory, you have a statement, you have to prove it. But there's a second phase. Is this the best proof I can give? You can ask the question, or maybe somebody else can ask that question. And so here you see people who asked that question and who gave different answers. Hey, there are different ways of proving this. And Jason Turaman hit the jackpot in my opinion. He provides the best proof. Elegant, nice. So he proves the result on the strict preference domain. There is at most one rule that satisfies my properties. So he proves something that's slightly more general. And since there's at most one rule, and we know one rule that does it, we know that TTC is characterized by those properties. So beautiful proof technique. It's a proof from the book. What's the book? Paul Erdős often referred to the book in which God keeps the most elegant proof of each mathematical theorem. So that's a mathematician. But you know, in econ theory we do some math, right? We can have beautiful proofs. So during a lecture in '85, Erdős said you don't have to believe in God, but you should believe in the book. I'm not commenting it, it's just a very nice citation. So if you have a grain of mathematician in you, you appreciate elegant and nice proofs. There's a thing that's called Erdős number. My Erdős number is 3, which is good. If I manage to write a paper with Laszlo Korsi, I can make it 2. So Laszlo Korsi is a colleague I had in Maastricht, and he, as an undergraduate, wrote a paper with Erdős, which gives him Erdős number 1. So if I manage to do something with him, I can lower to 2. It's not possible to go lower than that. So by the way, the Erdős number is a link. Paul Erdős wrote so many papers with so many people. If you co-authored with him, you have Erdős number 1. If you co-author with somebody who co-authored with Erdős number 1, they have 2. So if you co-author with me, you can have Erdős number 4. Let's go back to the Ma characterization. So you have a result, and you have a beautiful proof for the result. And now there's Akichi, Ozgun Akichi, who asks, do we actually need Pareto efficiency? Do we need the full extent of that? My continuation, if I have the time, will refer to that. Until when do I have? It's 10 now?
We have 1 hour, so 10:30.
Okay, perfect. All good. No. You just indicate when I have 10 minutes left.
10:45.
No, we are doing totally fine. I just don't want to rush. I want to make the link between the first part and the second part. My continuation has to do with this, and with the top trading cycles rule, of course. So Akichi comes and says, well, you know what? We don't need full Pareto efficiency. Full Pareto efficiency is about having all kinds of improvement cycles. You are not Pareto efficient if you have everybody in the room exchanging at the same time. That's a lot of people exchanging. So Akichi said us, well, you know, finding big improvement cycles in practice is hard. What about if people, when they bump into each other, figure out they want to swap? It would be really embarrassing if your rule violates not being optimal in that respect. So in other words, it would be really bad if I meet Cory in the floor and they said, you know, I'm teaching this math course, I hate it. And I said, you know, I teach this micro theory course, I hate it. And I'm like, I would like to teach math. And she says, I would like to teach micro. And we swap. And then we would complain and say, hey guys, let us swap. Everybody is happier. So detecting pairwise exchanges, and by the way, this is how the kidney exchange literature started, because patients who need a new kidney are taking dialysis. When they're in the dialysis, they talk to other people because they spend a lot of time. And they figure out, you know, I don't have my donor is not blood type compatible with me because he's A and I'm B. And then they talk to somebody with the opposite. And they figure out, hey, maybe your donor works for me and my donor works for you. So they can swap. So these swaps are very important in practice. Osgood figured out, well, you guess what? You can weaken perino efficiency to pair efficiency, where you just say, and I'm going to define it later, it shouldn't be possible that you get a better allocation by two people swapping. So this improves the characterization a little bit, because the top trading cycles rule is the only rule that satisfies pair efficiency, individual rationality, and strategy proofness. So that's a sort of better result. And then he got together with Jay, and they wrote an even more beautiful proof of that result together, adapting Jay's beautiful proof technique. So that also is 2024, very recent. Okay, so as you see, this was only part of a survey. This can go on. I can talk now about, and I won't, what are the extensions of the base model? The characterizations are for strict preferences. So what happens if I have indifferences? What happens if I'm not reallocating just one object but multiple objects? So I'm teaching a graduate course and an undergraduate course, and we have to swap within the categories. I have to swap my graduate course separately and my undergraduate course separately. What happens then? Of course, things get more complicated. So now people started working on extensions of the model, which introduce frictions and problems, and then they solve them, and then that's research. We push this further. Kidney exchange has its own challenges because there have been limits on how big the trading cycles can be. Incentives are not the same as here. You could have multiple donors that you present, but only one will be used. So you have many adaptations of the model that can be taken into account, and people have done tons and tons of research on that. So the little snail has reached the end, and with this we switch to the second part, if you're okay with that. So, yeah, maybe you can just do the switch. Let's breathe a bit before I jump into that. So the continuation, surprisingly, has to do a lot with this partial survey. And this is work I did together with a postdoc who is not in Lausanne anymore, Tom de Meulemeester. He's now at Maastricht University. So you see the feature already with the pairwise efficiency. The top trading cycles is not appearing in the title, but the top trading cycles insights helped find the result and motivated the research. We are not completely switching the object of discussion. The model is very similar. The notation is a bit different. Sorry, I didn't have time to merge the two presentations in the same notation, but it's a simple model. I'm sure you managed to follow me. So we are talking about allocation problems. I already mentioned they are very interesting, very important. But now we don't have endowments, right? So I'm not assuming that you own an object. We just have objects. And the objects could be school seats to students, internships, allocation of tasks, could be teaching without us owning property rights to the courses, and so on. Pareto efficiency in this context is the important efficiency notion. Remember, we don't have monetary transfers, and also we will not use monetary transfers in this context. And in this context, again, Pareto efficiency means no subsets of agents can swap, exchange their objects and be better off. So large improvement cycles actually might be very hard to detect. I already made this argument for kidney exchange, right? But the pairwise exchanges could be more easily detected because you run into a person, you talk, and you see, oh, we could swap. So the question is, under which conditions is preventing pairwise swaps enough to obtain full Pareto efficiency? So when do we have this connection that the pairwise improvements are actually going to be the same as any improvements are not possible? Now here is a list of papers just to again establish the fact that this is very related to research that people have done in the general equilibrium context at a time when also cooperative game theory was very popular. So this is just a list of papers where things have been done on the same question in the historical context of general equilibrium. But by the way, this was not my motivation. I only discovered these connections ex post after we had gotten the results. I'm going to tell you how this paper came about soon. And why I thought, oh, there might be an interesting result here. So, again, the model is super simple. We have a set of agents, we are in the room. We have a set of individual objects. For now, we assume that the number of agents and the number of objects is the same. I can drop it later. For the presentation, it's totally fine to assume that. We talk about the deterministic matching because later I'm going probabilistic. That's an extension you haven't seen yet, but that also can be done for top trading cycles. And so basically, deterministic matching allocation assigns an object to each agent. Okay. I'm assuming that agents have strict preferences. Again, in practice, I can make you give me a strict ranking. So you have to break your ties yourself. Notation is pretty much the same. The R is weak preferences, which means the object is weakly better. Could be the same, or it's actually strictly better. And P is the strict preference notation here. Again, a preference profile is a collection of the preferences of the agents. I need that as input, because I want to take preferences into account, right? And then my instance of the problem is the preference profile. I'm not going to change the objects or the agents, at least not in this talk. Okay, so a deterministic rule maps a preference profile into a deterministic matching. Now consider a rule that's very often applied, zero dictatorship. Well, dictatorship, but we need to refine that a bit. So suppose I fix an order of the agents, for instance seniority, right? We are allocating courses, so the person who is longest in the department gets to pick first and so on. You can use any ordering, or alphabetically. Assign the first agent their most preferred object. So basically the first dictator goes first, sees the object and says, oh, I'm taking this. I also brought some chocolate bars for organizers, so it would be like that. You fix a sequence and people sequentially choose their chocolate bar. And then once this person took the object and leaves, the second dictator sees the remaining object, picks the best from that, and so on. This is a very simple and very much applied rule. Okay, we know how it works. Here's still an illustration. So we have three agents. The sequence is 1, 2, 3. So you see that agent 1 goes first, he picks his best object. Agent 2 is lucky, his best object is still there. But agent 3 ends up with the worst object. And of course, there's a problem with zero dictatorship. Unless you have a sequence that everybody finds fair, people say, well, not people. The person picking last, I'm afraid this is my phone having some weird alarm. Apologies, I wasn't aware that that alarm was on. Let me just switch that off. I think that was from last week. The last person in the sequence might complain about the outcome, saying, that's not fair, I just get the leftover. So what can we do about it? Well, there's very little we can do about it unless we randomize, which we will do in a moment. So here's just a review of Pareto efficiency, which I already mentioned. So in this context, the matching is Pareto efficient if it can't be improved so that nobody is better off and somebody is, so that nobody is worse off and somebody is strictly better off. So the grand coalition cannot weakly block the allocation. That's Pareto efficiency. And the deterministic rule is Pareto efficient if it always picks Pareto efficient matchings. Okay. Strategy proofness. So by the way, I'm now repeating concepts I have introduced before. A rule is strategy proof if no individual agent can misreport and be strictly better off. So telling the truth is a weakly dominant strategy in the direct revelation game. We have group strategy proofness, which I have also defined for you. And the group strategy proofness again excludes deviations by groups such that the group members, some of them are better and nobody is worse. So it's this sort of blocking notion that's used here. Now I want to focus on groups that of a specific size, namely size 1 and 2. If we only allow pairs of agents to misreport, and this is not possible, and the rule is strategy proof, I will call it pairwise strategy proof. You can see that group strategy proofness implies pairwise strategy proofness implies strategy proofness. So we have a staggering of incentive properties in terms of their strength. Okay, now I do have to introduce the important notion of Muskin monotonicity, which has been introduced in the context of implementability. It is going to be very strongly related to group strategy proofness. For deterministic rules, it's equivalent. And that's important, but I need it for the probabilistic context, as you will see in a moment. So here's the intuition. First, we're going to talk about the Muskin monotonic transformation. The idea here is that I have a base situation, preferences, and a matching I'm looking at. And now imagine that matching, people think a little bit, so I have my preferences, I have my matching, and you think a little bit and you say, oh, you know, I realize my preferences are slightly different. I actually like this object I get even better. So this idea of people in principle liking the objects even better, and then the consequence that doesn't change the chosen matching, if you like something better, well, you still can have it. That's Muskin monotonicity. So the Muskin monotonic transformation at this matching could, for instance, look like that. And the intuition is the following. We are going to look at the upper contour set, which is the object itself at the matching and everything above. If you are shrinking your upper contour set, so that means the object you look at moves up. And that makes it better to you. Now the shrinking of the upper contour set is illustrated on the right side. So people say, oh, agent 1 says, listen, I think M1 is actually coming right after A. So you just shift it up, so B moves down. And the same happens for agent 2. He shifts M2 just below C. So it also got better. This guy here keeps it. Well, that already was his best object. And this guy here also keeps it. So this is a very simple shift. One thing that's also allowed is that while you shift objects up, you swap sequences of the objects above and below. And that doesn't matter. So your transformation is Muskin monotonic if it satisfies this, and the intuition is the matching M becomes weakly more preferred by all agents. Okay? So this is sort of the intuition of Muskin monotonicity. So by the way, William Thomson will, if he was sitting here, he would protest and say this is not a monotonicity property, it's an invariance property. Why is it an invariance property? For each preference profile R, and the specific matching that the rule chooses f of R, this is the matching I focus on, if your R prime is a monotonic transformation at the chosen matching, all agents get the same. And this here clearly is an invariance property. It's not monotonicity. He's right. But my probabilistic extension is a monotonicity property, as you will see. So I'm not switching names from invariance to monotonicity here. Okay, so this is monotonicity, and here are some results for our model, namely that monotonicity is equivalent to either pairwise or group strategy proofness. So I was just mentioning you for deterministic rules, it doesn't matter. Okay. Now let's go back to serial dictatorships. These are nice rules. Why? They pick something that's Pareto efficient. It's group strategy proof, monotonic. Well, I mean, nice. Wait, it's not fair necessarily. Last person always get the leftovers. So the last person, I mean, try this if you have kids. You know, if you say the oldest always picks first, the youngest at some point will start a revolution. So there is that problem. However, we can solve the problem by randomizing. You know, in the kids example, you could take turns. You know, everybody is the first dictator once, second sometimes. So basically the idea is you are just uniformly randomized over all orderings. So everybody is picking first, everybody is picking second, at the same frequency in practice, probabilistically equally in our context. So you use a uniform distribution over all sequences. So if you do this for our simple example, you get, for this example, if you just go through the 6 sequences of the 3 agents, what you get is that you get a lottery allocation where A, C, B, you know, the color coding is first choice, second choice, last choice by green, orange, red. With probability 1/2, you choose this outcome. With probability 1/3, it's this one. And with probability 1/6, you choose this one. So you see, yes, agent 3 gets his worst outcome with probability 1/3, but he can also get his best and his second best sometimes with a certain frequency, and that depends on your preferences. So random serial dictatorship implemented either probabilistically with lotteries, with lottery tickets, or actually with frequencies is a nice thing that people do. Now with this we go to lottery rules. So we extend our context to so-called lottery rules. A lottery is a probabilistic distribution on deterministic matchings. You have just seen a lottery on matchings. A lottery maps each preference profile to a lottery. By the way, in case you have looked into these probabilistic allocation mechanisms, you can look at lotteries or you look at the bistochastic matrix that maps into the marginal utilities, and then you can do things with that. We don't. We just look at lotteries. So we denote by phi matching M of R the weight, the probability assigned to matching M in the lottery. Right? So the lottery rule is phi, and then this here is the probability that the lottery rule assigns to matching M. So you saw these probabilities here. And all matchings that are not here have probability 0. Why would I denote them if the probability is 0? And then the support of a lottery are all the matchings that have positive probability. So here the support is those 3 matchings, not the others. They have 0 probability. Okay. So this is a way of extending this. Now what are my properties? How can I extend the properties? That's easy. I can go for exposed properties. So I can say a lottery rule is exposed Pareto efficient if it only puts positive probability on Pareto efficient matchings. It never chooses a matching that's with a positive probability that's not efficient. What is the probabilistic version of monotonicity? There's a very natural and beautiful extension proposed by Christian Bastek, who you see in the next slide, or the next after. Suppose that again your matching M in agent's preferences becomes weakly better, meaning I have a monotonic transformation. What we want is that that matching then is chosen with a probability at least as large as before. It's a better matching, maybe I want to put more probability, but at least the probability doesn't go down. So that's a monotonicity property, right? So I have a matching, it has a probability in the lottery, it becomes more popular. If anything, I should choose it more often. Very natural. And that's just encoded over here. Beautiful characterization of Christian Bastek. A lottery satisfies ex post Pareto efficiency, probabilistic monotonicity, and equal treatments of equals if and only if it's the random serial dictatorship rule. I didn't tell you what equal treatments of equal is. I'm not going into technology here unless you beg me. What does it mean? Corey and I have the same preferences over objects. Turns out we have exactly the same preferences. So now if there's a matching chosen, where she gets an object and I get another object, the matching where we swap these two objects has the same probability. That's equal treatment of equals. Because we are the same. So if we permute the matching and the matching just swaps what she has and I have, that match and you get the same, it should be chosen with the same probability. It's pretty natural extension of equal treatments of equals. So that's Christian's result, very recent. Now we started thinking, that's the origin of this, and I'll tell you why. Can we relax ex post Pareto efficiency in this characterization to pairwise, ex post pairwise efficiency? So, and the answer is going to be yes, but actually we get more results. This is the initial research question. And this is pairwise efficiency. You have encountered it, but here you see an example of a situation where the green matching actually is pairwise efficient. Yeah. BCA is pairwise efficient because when two agents swap their objects, one gets better off and one gets worse off. This is sort of a Condorcet cycle example, which is why this works. But it's not Pareto efficient because, as you can see, everybody can get the best object. So this illustrates that these are different concepts. Pareto efficiency is stronger than pairwise efficiency. Just make agents in the green matching, make agents 1 and 2 swap, then agent 1 is worse off. It's not better. So any swapping results in somebody where somebody is very unhappy. So I already made this point while we look at pairwise efficiency. So we can look at ex post pairwise efficiency. All good. All very good. So that's what we do. Now, why did I have the idea that this could actually work? Remember, my research question was, can I weaken this? But why did I even have that idea? So this is a little bit about connecting different literatures and forming a hypothesis of what could be true, because you see, oh, something happens here, I wonder if it could happen here. So I observe something in the deterministic world, and I happen to know another result. So this is about knowing the literature, and that's completely applicable to other fields. Know the literature, have a bit of a broad spectrum, and then you see patterns in different parts of the literature, and you ask, can I combine them? Is there something here that I can put together, like pieces of a puzzle? And here's the other piece of the puzzle I needed to make the connection, a result by Abdul Kaduropoulos and Sönmez, because we have talked about taking a lottery rule over the serial dictatorships, equalizing the probabilities of the sequence. Now, if you now go back to Shapley-Scarf housing markets where we own an object, so those guys ask the question, I know I don't have really endowments, but what if I randomly assign endowments to you? I have my objects, equal number of objects and agents. What if I give each an object and then I let them trade according to TTC? And now I'm randomizing that. I give you the endowments with equal probability. So I look at all possible endowment allocations, and then I apply TTC. And these guys figured out, very beautiful result, that TTC with random endowments produces the same lotteries as as the random serial dictatorship rule. So randomly allocating endowments and letting people trade is the same as running serial dictatorships with equal probability. Beautiful. These results have been later even more extended. No time to go into that. But when I connected that puzzle piece with Christian's characterization, I thought, so wait a second. So here's the thought line. If random serial dictatorship is characterized by Pareto efficiency, that's a serial dictatorship result. But serial dictatorship is also random TTC. And in characterizing TTC, we can use pairwise efficiency. Can I use pairwise efficiency to characterize random serial dictatorship? You see the puzzle pieces that are now put together. So that's how I started the research, thinking, oh, we need to check this. Okay, this I don't need to go through with you because you just saw that in the first part of the lecture. So here I have the characterizations. I made the connection and now I can move to the main result, which is not, the main result is not weakening the one assumption in Christian's characterization. We got more. We set out to do one thing and then we got more results. And that often happens when you do research. You want to do one thing, but if you keep an open mind, you might find more than that one thing. You might find more results. For any lottery rule satisfying probabilistic monotonicity, exposed pairwise efficiency implies exposed Pareto efficiency. So once you have the monotonicity, this follows. Now, I want to mention, next thing we did is, do we need to have the same number of objects and agents? Which I needed for the TTC connection, but turns out I don't need it. It can be more general. So now I assume that the objects can have capacities more than one. Think about school choice models or university assignment. You have multiple seats in a school. It's not just one student consuming one school. There are many students going to a school and the school has a capacity constraint, or universities. So objects can have capacities larger than one. Now I need to do one thing. I need to talk about non-wastefulness, because if I have many objects, I could just withhold objects and never allocate them. The University of Reus is not taking students. I don't want to do that. So I talk about exposed non-wastefulness. When is something wasteful? It's wasteful if you have a matching and Corey looks at the matching and says, Bettina, I get this milk chocolate and I see that you have dark chocolates left over that I want, that are not allocated, give me a dark chocolate. So I would have waste if I don't allocate these objects, so I shouldn't have that happening. So I don't want non-wastefulness for deterministic matching. Exposed, I don't want probabilities on matchings that are wasteful. So that means there are objects not allocated that agents actually want. I don't want that. So non-wastefulness, oops, wrong clicking. Non-wastefulness pertains to improvements of single agents, taking an object that's not allocated. Pairwise efficiency improves the allocation to pairs of agents by swapping. And Pareto efficiency improves subsets of agents. Remember, for strategy proofness, you had group strategy proofness, pairwise strategy proofness, strategy proofness. Similar ranking of properties. So now our main result is for any lottery rule satisfying probabilistic monotonicity, exposed pairwise efficiency, and exposed non-wastefulness implies exposed Pareto efficiency. That's the result at the key, at the heart of the paper. What is implied? First of all, indeed, we can improve Christian's characterization a little bit by weakening Pareto efficiency with pairwise efficiency. Strictly speaking, this weakens and strengthens the theorem because it's an if and only if statement. But of course we know it's sort of an improvement in this context. So we improve this result, but we get a bit more than that, because remember that a deterministic rule is a degenerate probabilistic rule, right? A deterministic rule is a rule that puts probability one-on-one matching and zeros on all others. So now the exposed properties become the original properties for deterministic rules, and we actually get, since monotonicity is equivalent to pairwise or group strategy proofness, for deterministic rules we get the result that if the deterministic rule is pairwise strategy proof, then pairwise efficiency or non-wastefulness implies Pareto efficiency. So for deterministic rules we have that. And now we can say, hooray, there are many papers out there, I just give you 2 examples, where group strategy proof and Pareto efficiency are used together. So there is a paper by Marek Piche and Utko Ünver in theoretical economics where they characterize all rules allocating objects that are Pareto efficient and group strategy proof. Doesn't matter what they call this class of rules, I'm not introducing them to you. Point is, our results tells us we can weaken the properties of the characterization. Previous paper by Sylvia also characterizes a set of rules that are Pareto efficient group strategy proof, plus some property that I don't want to introduce because it takes time and it's not important. Because the point is, we can strengthen that characterization. Actually, this is a recipe for any result that has group strategy proofness and Pareto efficiency. You can now do this everywhere. You can just refer to our paper. I mean, I'm not sure if you're going to do that for this type of model, but any person who was working on an object allocation model having group strategy proofness and Pareto efficiency can now just say, listen, you don't need properties as strong as that. You can have the 1 agent and the 2 agent properties, and that's enough. And I'm not sure why this shows up. I should have checked my slides. Anyways, I have reached the end of this part of this second part. I hope you enjoyed seeing how some of the research results were obtained, even though the results themselves might be a bit far away from what you are personally doing. But again, I thought it's also a nice idea to show you how research is done, what is the motivation, how do you put things together, and I think that is pretty much context-free, so that you can apply in your research as well. And I'm very happy if we have the time, if you have some questions or comments, to take those. Thank you very much.
Thank you very much. Thank you very much for this beautiful talk with a nice survey, and also this history about Scarfangale, which I didn't know it, so it was fun.
Exactly.
Thank you very much, and the new results also, so you did a good job. Thank you. If you have any questions?
We can also take it offline during a coffee break. I'm going to be around, huh?
Yeah.
Yeah, I have a quick question. I'm not into this topic, but in the first part of the lecture, you went a bit fast through the breaking ties stuff. You said
yeah, totally.
Yeah, okay. So you said that if you have a tie, then you randomly break it, however, right? But then, I mean, I'm not into this topic, and I'm speaking from the outside option, let's say like this, but I feel like this is making someone worse off, because in your example, where we had 30 people, right?
This is an excellent question.
Thank you. Right, so you have 3 people, and then 2 of them exchange their house, but the green one was pointing at the second one.
Yeah.
So that guy is worse off, and then something falls apart. Or what happens here? What do you think?
Yeah, so the point, and this becomes very relevant, for instance, in school choice problems. School choice problems are allocation of objects to students' situations. And in fact, this is what I was very quick, because it's limited time, saying, well, you know, I'm looking at strict preference because then results are particularly nice, and I can sort of continue with this, and in practice I can make you break ties, you know.
Okay.
Now in school choice, sometimes ties are broken either for the preferences, honestly very much forced they do force strict preferences sometimes, but sometimes they break ties with priorities, which is a very similar thing. The thing that happens with breaking ties forcefully in the preferences, you lose some of the efficiency properties, right? Because maybe I make you strictly prefer a Coris Maths course, but actually you would happily take another course. The moment I break the tie and I give it to you because now you have a high, I see you like it, but it's actually not really true, I might create something that's not pretty efficient anymore. So you might be losing some efficiency properties due to that. Once you want to take it fully into account, as I mentioned, weak preferences impose problems. A lot of the nice results don't hold. There are extensions of top trading cycles into weak preferences. The problem has been solved. There are versions that make it efficient, but the algorithms become computationally more complex. So again, it's just a partial survey, but then is one of the directions where research has been done and should be done. It just gets more complicated. But again, these are the questions you ask when you see a benchmark result, which has certain assumptions. What happens if I don't have that assumption? What are the problems? How do we solve these problems? And then it leads you further into research in that direction. But it's an excellent question.
Thank you.
More questions?
Yes, could you please re-explain why it's interesting to replace, for example, in the results of Papai, etc., why it's interesting to replace the Pareto efficiency with the non-wastefulness, etc.?
Now, there are two reasons. I mean, one is a purely theoretical one. You have a stronger result.
Okay.
Right? So, because you could say, fine, you know, if I want a solution that's Pareto efficient, individually rational, and strategy proof, I'm going to the deterministic context now. I have to do top trading cycles, right? So that's the only way of doing it. I don't debate, right? If you want these properties, that's what I do. Or maybe somebody says, I wonder, yeah, maybe there's something else we could do. And you know, I'm not so concerned about full efficiency. I just don't want people complain about the allocation when they bump into each other. So what other rules do I get when I make this assumption weaker? Okay. Right? So I say, fine, I want to see other rules, weaken the assumption. I just want that people don't complain because they talk to somebody at the water cooler. Okay. And now the answer is, I'm sorry. If you do that, you still get the same. Okay. Unless you compromise on the incentive property or on the individual rationality property. So there's a theoretical interest because you make the characterization stronger by having weaker properties. And the practical interest is, so the idea of this normative characterization of rules is that in a practical context, when you really implement, you might ask people, what are the properties you are concerned with? Is it efficiency? Is it what type of incentives? What are the desiderata that you have for the allocation mechanism that you have in mind? And the person might tell you what is important in the context, right? What do they care about? And then the exercise of the market designer is to think about what are the possible mechanisms that I can offer to you. And as soon as you introduce some other things, if you find one property more important than the other, you get different mechanisms. And this research in characterizing and seeing what the trade-offs are helps you make recommendations in those contexts. In school choice, so school choice allocation mechanisms in the US, for instance, is a huge application of, for instance, top trading cycles versus another matching mechanism called deferred acceptance. And then the recommendations, the context matters for your properties, so we can talk about it later.
Okay,
I don't want to talk too much about that. But then you get these discussions, which mechanism should you use and why?
Okay.
Okay. So thank you. There is a coffee break outside, I think so. Right?
Excellent.
So we can...
Coffee is good.
Okay,